I lost my day yesterday.
It's a postbox thing.
It's a postbox thingy.
Oh,
Friday.
until 9 AM on Saturday.
Wait, what?
That's not how that
Do you?
Yeah.
Really?
Well,
Well, yeah. We don't collect it till the day.
Then again, I've got work at like 12:15.
Yeah.
So
Mine will be on Friday. Don't know, not done.
yeah, same.
anyway, I'll be in tomorrow. Well, tomorrow, yeah, I'll be around tomorrow morning. Tomorrow evening, we've got a big meeting, so it might be tomorrow afternoon. Thursday, I'll be in for most of the day. Good availability as well, if you need to come and find me.
I may have to come in here so there's no distractions at home.
Okay, so lemma 13.8. Remember, we're on our way to proving the fundamental theorem of finite abelian groups. And 13.8 is a stepping stone towards that. The fundamental theorem of abelian groups says any group, any finite abelian group is a direct product of cyclic groups of prime power order. This is going to show that G is equal to the internal direct product. G is equal to the internal direct product of G1 times G2. Well, let's say isomorphic to the internal direct product of G1 times G2. Let's just repeat the notation we had yesterday up to GK. Okay. And the K is coming from the fact that N, which is equal to the order of G, we think of that prime factorization. So this is the prime factorization of N, which is the order of G. Typical prime factorization. So there are K different primes that divide N. And for each of those primes, we've got one of these groups, GI. This is an internal direct product. So G is isomorphic to the direct product of these, but G is actually equal to just the plain set-wise product of these. Okay? Because these are all subgroups. So the GI is defined to be the set of all the elements from G such that the order of G is some power of PI. Some beta. Some beta. Okay. Obviously an integer. Beta is power. And, okay. And this is called a primary component. Primary component of G. With respect to the prime PI. Okay. Previous lemma told us that for any prime dividing the order of n, so for any of these PIs, G does contain at least one element, therefore multiple elements. G does have elements of order PI. Okay? So these GIs, each of them are non-trivial. Okay? So there are non-identity elements around in G which have order various powers of PI for each of the primes PI dividing G. Now, yesterday, we talked through the proof of this, and we got up to proving okay. So yesterday we proved the GI are subgroups, and they have the necessary pairwise trivial intersections. And what does that mean? It means GI intersect GJ, well, they're subgroups, so they do have some intersection, taking at least the identity element, but their intersection is only the identity element when I is not the same as J, and we're talking about the two different ones. So they all have trivial intersection. This means that their set-wise product, G1 times G2 up to GK, is an internal direct product. So it is isomorphic to the direct product of them. Okay, they're formally different things. This thing here is just a subgroup of G. Okay, it's just the set of all the products all elements in G that can be formed as a product, one element from G1 times one element from G2 times one element from GK. So the set-wise product of the sets. This is isomorphic to their direct product. This is formally a different structure because this thing consists of vectors of length K, one component from each of the groups GI. Okay. So what we're missing to show, so that's just what we proved yesterday. And then there's a gap in the printed notes that I communicated with Judson about. It turns out it was in a previous version of the book, but it somehow got omitted when they redrafted the book or redid the book, and so he's since reinstated it in. So the next year's version of it, the book should have this gap filled again. So the gap is, at the moment, it could just be that this is some subgroup, some smaller subgroup of G. But we want it to actually be equal to G. Okay. So what's left to prove is we now prove that this, meaning this subgroup relation, is actually equals. Okay, so that the set-wise product of all of these is actually the whole of G. Okay. Is everybody okay at the moment about getting up to there? Okay, so we need to show let G be any old element from the group G, and we will now construct or directly show that we can write G as a product of elements. We will show that we can write G as G equal to G1 times G2 times GK, with the GI belonging to capital GI. Okay, so we need to find a set of elements G1 to GK. Each little GI has to have order some power of the prime PI, because we want it to be in the ith primary component. Yeah. Clear? So where are these elements going to come from? Where can we find these G1 up to G little k? And this does seem quite tough at the moment, because all we know is we've just got this G, this element little g. So where are we going to find these GKs? Where are we going to find these GKs? Well, they actually come from G itself. There's a neat little, I'd almost say a trick, but there's a neat little construction that we can follow to get these, okay? So we define, remember n is the order of G. So n is the product of all the prime powers, okay? We define ni to be n divided by pi to the power alpha I, okay? So from n, you take away all the primes pi, and that gives you your number ni. So in other words, you can also write this as, so ni is the product of all the pj to the alpha j, from j equals 1 up to k, but except for I. So you leave out the ith prime. Does that make sense? Yeah. And we can form that by taking n, which is the product of all of those, and just dividing it by the ith power to remove it from the product. What can we say about all the ni's as a set? Notice that
pairwise co-prime.
not pairwise co-prime. So if I take any two of these, they've got a lot of primes in common, don't they?
Oh, yeah.
See, because n1 is everything except the p1 to the alpha 1, but it's all of the other primes. And n2 is everything but the p2 to the alpha 2. So there's a lot in common between n1 and n2. So they're certainly not pairwise co-prime. So not by pairs, but we take them all together as a collection. What's their GCD? We take all of them. GCD of a collection is defined just in the same way as the GCD for pair. So what's the greatest common divide, the greatest number that divides all of them? One, yeah, exactly. Because there's no, you won't find any primes that are common to all of them.
We've got at least one.
Exactly, they've all got one missing, yeah. So the candidates for the GCDs have to come from products of these primes, yeah. But each one has a different one missing. So there's no primes that divide them. So exactly right, you're left with a GCD as well. Now, what did we learn in number theory as a direct consequence that we often call upon when we encounter co-prime pairs or co-prime sets of numbers? It's a very common move. If ever we encountered an A and B that were co-prime, immediately move to something else. Yeah. A linear combination of the numbers equal to their greatest common divisor. And you can do it for two numbers, you can equally well do it for sets of them. So that means that there exist coefficients, integer coefficients, what we call them gamma i's, say, such that when you take the linear combination of these, it's equal to 1. Great. This I equals 1 to k. Okay, this is what we call Bezo's identity. Remember that? Okay, we normally encountered it for just a pair, but equally well it holds for any number. And this gives us a really interesting way of writing 1. Okay. So remember, this is what we're trying to prove. We're trying to prove that G is equal to this, that we can find these elements Gi. And here's where they come about, because G, which is equal to G to the 1, and we take this interesting way of writing 1. Okay? So this is G to the sum of the gamma I ni. And what does your rules of indices tell you about where the exponent is a sum of things? Multiplying the individual powers. Yeah. So this is the product of.
It's evil genius planets consequential.
No, but it's going to come back to a similar form of the.
Yeah. So our G to the gamma 1 n1 times G to the gamma 2 n2 times G to the, and it ends with gamma k nk. Okay. This is equal to G. So we can think of G as the product of all these various powers of G. And this expression up here is what we're going for. So this is the candidate for it. Okay. What happens? Notice that if you take one of these, the G, you take G to the gamma I ni, and you raise it to the power p to the I alpha to the I, what happens? What's that equal to? Remember, these are supposed to be elements of the primary components. Yeah, so why is it the identity? How can you claim that that's the identity?
Because you divided out the pi and the ni, and then you're multiplying it back.
So we're sticking it back in. So, yeah, so just by rules of indices, this is G to the ni, gamma I ni, b to the I, alpha I. What was our definition of ni? Remember, ni was n divided out by p I alpha I. So when you multiply it back in, this is n. Yeah. So that's G to the gamma I n And that you can reorganize as G to the n gamma I. N is the order of the group. So everything has order dividing n. So every group element to the power n is the identity. Can you see that? So that's e to the gamma I, so that's e. So what does that tell us about the order of this element?
Yeah.
Maybe not exactly. It could be that this is a multiple of the order. Yeah. But if we ever see a group element to some power equal to the identity, then we know that that power is a multiple of the order, and that the order of the group element divides that exponent. Okay. Remember, the order of an element is when you cycle around various powers, and it's the first time you arrive back at the identity. But if you raise it to a power a multiple of that, then that just means you zip round the cycle a number of times and you finish back at the identity. So this could be zipping round the cycle for this element a number of times. Okay. So the point is it must divide that. So this divides EI to the alpha I. So that means it's equal to, what are the divisors of PI to the alpha I?
PI to various powers.
Yeah. So PI to some power. So it's PI to the beta for some beta. Okay. It can't be any bigger than alpha I because it has to divide it. Yeah. So it's some power of, sorry, beta. Yeah, some power of PI. So that means, i.e., G to the gamma I mi is an element of the ith primary component. Okay. The ith primary component contains all the elements from the enclosing group G that have power, some power of, that have order, some power of PL. Okay. So that implies that G is an element of the set-wise product of all of the primary components, doesn't it? Because we took the element G and we were able to write it as a product. In this funny way of writing one, we saw it as a product of all these powers of G. Each one, each factor there, is an element of GI. So G is contained in the product G1 up to GK. And little g was, at the start when we introduced it, little g was just any old element of G. Nothing special about it, just any old element of the group. So that implies that the G is contained within this product. But we already know that that product is contained within G, so it's a product of subgroups of G. So therefore, this must be equality. Yeah. Equal to G1, G2, as far as GK as required. It's actually equal to it, okay? Because every element can be expressed as a product with the various factors coming from those. And just remember, this is isomorphic to the direct product of them. So we've already proved that they have the necessary trivial intersections properties so that the set-wise product is an internal direct product. So it's isomorphic to the direct product. So that finishes off the proof. So that's the gap, that argument that wasn't included in the version of the proof we have in the notes. Because in the notes, he gets to this stage here. So here, he concludes that the product of all the G's is an internal direct product. And then he just immediately jumps to saying the size of it is the size of G, and therefore it's the whole of G. But it's that gap in this proof that needs to be resolved. So So that's what we've achieved. Is that okay? Is any questions about that? And that's more or less the argument that Judson's reinstated there. So how close are we to proving our fundamental theorem of finite abelian groups? Well, we've got it down to this now. Given any finite abelian group, so just looking back to the statement of this lemma, we can write G as a direct product of these primary components. And each GI is what we call a P group. It only consists of elements whose orders are some power of the same prime. Yeah. GI consists of all the elements, all its elements have orders some power of a particular prime. PI, GI.
So the prime is always the same, but the beta can differ.
The beta can differ for different elements.
Right.
Yeah.
But the PI is unique.
The PI is attached, see, it's the same index I.
Oh, right. Oh, yeah.
Yeah. So G1 is where it's featuring the prime P1, the first prime that divides in the prime factorization of it.
Mm-hmm.
G2 is featuring the prime P2, whatever the second prime is that features in the prime factorization of it.
Right.
So it all grows out of the order of the group and the primes that appear in the prime factorization of that.
Right.
Yeah. Okay. Then you've got one of these, what are called primary components. You've got one of those for each of the primes that appear there.
Yeah. Okay. Yeah. I just, because of missed yesterday.
Yeah. And as a consequence of that theorem, what we've also seen is NB, we've shown here, or we can deduce from this. Because how big is G? If G is a direct product of these, the size of G is the product of the individual sizes. We already know from a lemma that the size of any of these P groups is some power of the particular prime. So it must be now the full power of it. So that the size of GI is PI to the alpha I. Where the alpha I is the same alpha I that appeared in the prime factorization of it. The size of GI is PI is PI to the alpha I. So remember, the fundamental theorem of abelian groups says, so I'm just putting the statement of the lemma down there again, says that G can be written as a direct product of cyclic groups, each of which it has prime power order. Now we can see what we've achieved so far as G can be written as a direct product of P groups. So now what we need to know is that if you take each of these P groups, you can write it as a direct product of cyclic groups, each of which have order some power of that primes corresponding to, associated to that GI. If we know we can do it for a P group, then we'll just do it for G1, we'll do it for G2, G3, do it to GK. We'll have each of those as a direct product of the necessary types of groups. So then G will just be the big, long direct product that you get from gluing them all together. Okay. So that's what our lemma is now. Our lemma is going to show that if you take one of these GI, that it can be written as a direct product of cyclic groups, each of which has prime power order. Okay. So that's lemma 13.9. We can at least look at the statement of. We may or may not get all the way through the proof of it. Today. So lemma 13.9. So we're thinking that we're going to apply this to each of the capital GIs on the previous lemma. So we let G be a P group. So we're dropping the I, and we'll just now focus on the case of a group, which is like one of the GIs. So it's a P group. So i.e., it just consists of elements whose orders are some power of that prime. And suppose G, little g, is an element of G with maximal order. There's a subtle difference here, but we don't say it has maximum order. If we said little g has maximum order, that would mean that of all the elements in capital G, this one is the biggest order and it's biggest than all the other ones. Right? Saying something as maximal order means that there might be a load of elements here, all with the same order, which is maximal over all the other elements of the group. So there might be many candidates to choose from in the all of order 25 or something. So there isn't a single unique one with order 25, which is bigger than all the other orders. There'll be a bunch of them. Again. So we just choose one of them. Okay. So it's not implying that the order, it doesn't mean that the order of G is strictly bigger than the order of every other element. It means greater than or equal to the order of every other element. Exactly. Yeah. There's no other element in G with order bigger than this little g. It's got maximal order. Then the conclusion is that G is isomorphic to cyclic subgroup generated by G and a direct product with H for some. So this is an internal direct product. These are subgroups of G. And for some subgroup G of H. Sorry, H of G. What's the size of this cyclic subgroup generated by G? Well, you see capital G is a P group. So every element has order some power of the prime P. So the size of this G, brackets NB, the size of this cyclic subgroup generated by G is some power of P. So i.e., the cyclic subgroup generated by G is ZP to the beta. So this is one of those factors that the fundamental theorem of finite abelian groups says that G is a direct product of. Yeah. So this is where we generate this. This lemma is the one that actually sucks them out. Okay? It shows that they're there. So we'll do the proof next time, because I don't want to. There's no point in racing through it because then it just goes by in a blur. But what we will do now is complete the proof of the theorem. So if we take this on faith for the moment, right? So then we'll show how we just put all those lemmas together to prove the theorem. Okay. So what we can do here is the proof of the theorem. Okay. Fundamental theorem of finite abelian groups. So by lemma 13.8, so let G be a finite abelian group. We know G is isomorphic to the direct product of its primary components. That's lemma 13.8. Okay. For each I, Gi is isomorphic to this thing cross H. So this is applying lemma 13.9. So this is actually, it's Z Pi to the beta, direct product with H for some beta. Now, what kind of thing is this H? It's a subgroup of GI. What kind of group is it? It's again a P group. H is some of the elements of GI. So every element in H has order some power of PI. Yeah. So NB, H is again a PI group. A P group, but reference to the prime PI. So lemma 13.8 applies to it again. Okay. So apply 13.8 to H. And then we'll get that GI is isomorphic to Z PI. Ooh, let's just put a 1 on that beta there, some beta 1. The beta 1 cross Z, still PI, but now it's to a beta 2. Oh, let's put a 1 on that H. And then there's left behind a H2. So this is now for some beta 2. You see what's happening? And this, I mean, we've taken account of more elements of GI. So this H2 must be a smaller subgroup than the H1, yeah? H1 is smaller than GI because we've separated off some amount of the elements of GI, yeah? So these subgroups are getting smaller all the time, so you just keep going. So basically we're applying Dutch. Yeah. So NB, the size of GI, whatever it is strictly bigger than the size of H1. That's strictly bigger than the size of H2. So keep going. Keep going until we have our ith primary component as Z PI to the beta 1 across a load of these Z PIs, and then in some case we'll get a beta R, we'll get a last one, and the subgroup H will actually be the trivial subgroup. So if you like, you could have cross with the trivial subgroup, but you don't include the trivial group as a factor in the direct product because there's only one. It's like adding on an extra position to your vector, but it always has one in it and nothing else. That doesn't add anything to the description. Okay, so you can just leave it off. It's like the equivalent thing to writing in a factor of 1 in a product of integers. 5 is equal to 5 times 1. But
Implied.
yeah, it's implied. Yeah, and it doesn't gain any extra information. Yeah. So eventually this process will end of separating off these cyclic components of prime power order from GI, repeatedly applying lemma 3.8. Eventually it's going to stop. So we can do this for each of the i's. Okay? So each of these turns into a direct product like this. So then simply, this is one of my favorite words, concatenate all these to get the required expression for G, which is demanded by the theorem, which says G is isomorphic to direct product N of Z's QI's to the gamma i's, or primes QI, not necessarily distinct. Normally we're used to from number theory, whenever we see products of primes indexed by things, we normally take that the primes are distinct, but in this one it's not. The prime PI is repeated in a number of positions in the direct product expression for the ith primary component. So this is for primes QI, not necessarily distinct. This was the kind of expression claimed by the fundamental theorem of finite Abelian groups. Okay. Concatenate just means join the lists, one list after another. You know. Each of those components splits apart as this direct product, so you just concatenate them all, and you get them. Okay. So that's how the lemmas get pasted together, if you like, to prove the theorem. Okay. So that's the end of the proof. Does that make sense? Yeah. So that finishes the proof, except for we would like to see why lemma 13.9 is true. Okay. So we'll come to that next week. Because 10 minutes is enough to do it justice. It's not that long, but there's a number, not so much. No, they're not gaps in his proof, but there's a number of points that he kind of skips over, maybe jumps over. So there's a couple of expansions of explanations there that I'd like to say something about in his proof of it. So any queries just about understanding the whole thing and fitting it all together? Okay.
I think with me it takes about a year to process, so.
I mean, you know, it does take time to process. Like I've been living closely with this stuff for like at least 3 or 4 years, just in terms of putting the unit together and just, you know, thinking about it all again.
So it's been one interesting thing about you, Killian, is that you just come to the lectures and you know exactly what you're going to write.
Well,
It's always been like.
There's over 3 years, and there's 3 times where he forgot, and like he gets stuck for like a good 10 minutes.
That's what, yeah, and that's.
well, okay, yeah, that happens.
So that's like when that happens, that's funny. But the other times when it's just being rinsed page after page, it's just like, wow, you must know this inside out. Yeah.
I mean, I hesitate to say it, but it is easy when you know how, because you know it all does. It's just like a jigsaw, and it just all fits together, and each bit goes to the next bit. I mean, I don't know. That's. I mean,
yeah, when you kill
that's
it.
cheap. No. It's the same thing as saying like hindsight is 2020. You know, we can easily see now that the decision to hold the Brexit referendum was a complete disaster because we're looking back at where we are now and what we've come to. It's the same way like that. It's finding these proofs for the first time. It's finding the arguments for the first time is the tough thing.
Yeah, that's
solving a problem when nobody has laid out the path before. Yeah.
Well, that's what this book does, but obviously, like you're just giving, you're sort of like spoon feeding it very systematically in the best way.
But like that's
the
the main way of
that's exactly it. Laura's just actually took the words out of my mouth. We could not read this book without a form of interpreter.
Well, okay, fair enough. I mean, I think you could. Just maybe take you long. You just need to think.
You give me more credit than I do.
Deeply about it.
Me in particular.
But what is left for us to do, of course, so the proofs are all very well explained here. But there's all these exercises, okay? So we looked at some of them on last Friday. So we'll look at a few more of them on in this Friday's tutorial. And build a few arguments. Okay? Or maybe look back at previous exercises.
I don't know that. I was on here Friday.
Who was here on Friday?
No, didn't you?
I was writing digital.
You would have been
Just
busy.
James and the land, was it? It was just you two.
Yeah, I can't remember. We did. My brain just died.
Well, we did some of these exercises.
Yeah.
And maybe Jordan was there. Or
I wasn't there on Friday.
I was there, but apparently only in physical body, not in spirit.
What? I completely can't remember how Friday went.
okay, so anything on the coursework then? You know, just want to give you. We've got a few minutes.
I've got one about about 2 hours working on it now.
Yeah.
On a break.
I'm going to be spending about 3 hours on it, yeah. Oh.
And then all of Wednesday, all of Thursday.
Can't spend Wednesday on it, all of Thursday, indefinitely.
I felt really good. I thought I was going to get it done early and get it like latex. So,
Yeah.
and then I've run into the issue that's not going to happen. With my handwriting, which I'm really upset about. But I've got to point with latex now. It's second nature. Unless I have to do something really crazy with some figures and move them and scale them and change the boundaries and stuff, I'm